The focus of this video is going to be one of our Unit 8 topics, and the topic is the area of a region between two curves. There are 3 learning targets that go with this particular topic. Finding the area of a region between two curves using integration. Finding the area of a region between intersecting curves using integration. And describing integration as an accumulation process. There's a link to a Khan Academy video as well, and if you hit Control and click, it will take you to the video, and it's a nice addition to what I'll be talking about in this video if you choose to watch it. It's not too long, 4 minutes. And he does a nice job of explaining how it works. My goal is to do the same thing. So if I go to the Unit 8 notes, here's the definition of the area of a region between two curves. I'm going to read it. With a few modifications, you can extend the application of definite integrals from the area of a region under a curve to the area of a region between two curves. Consider two functions, f and g, that are continuous on the interval from a to b. If, as in figure 7.1, the graphs of both f and g lie above the x-axis, and the graph of g lies below the graph of f, you can geometrically interpret the area of the region between the graphs as the area of the region under the graph of g subtracted from the area of the region under the graph of f, as shown in figure 7.2. Here's figure 7.1. As you can see, both the f function and the g function lie above the x-axis, and the f function is above the g function over the interval from a to b. So if we took the area of the region just under f, it would be the region underneath the bolded curve. As you can see, I'm scanning over here. And then if we separately took the area of the region under g from a to b, that would be the area underneath here. So if we took the area under f and subtracted the area under g, it would give us the remaining area between the curves. So, to find the area between two curves, you take the integral over the region of the top curve minus the bottom curve. As is illustrated here, the area of a region between two curves. If f and g are continuous on the interval from a to b, and g of x is less than or equal to f of x for all x in the interval from a to b, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is the integral from a to b of the f function minus the g function with respect to x. On the back of the Unit 8 curriculum map, this is highlighted here. The area of a region between two curves, f of x and g of x, where f of x is greater than or equal to g of x on the interval from a to b, is the integral from a to b of f of x, the upper function, minus g of x, the lower function, with respect to x. Examples are always helpful. So without a calculator, find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. first thing I'm going to do is get myself a coordinate plane. And I'm going to be strategic about how I make my coordinate plane here. So here is my x-axis. Here's my y-axis. And I'm only concerned about the area of the region bounded by the two functions, and then x equals 0 and x equals 1. So I need a sketch of these graphs, and I guess I probably should have been a little more accurate when I was creating this, but I'm just going to improvise. I'm going to call this y equals 1, y equals 2, and down here will be y equals -1. And if I was to draw a sketch of these, I really only care about the region, I should say, between x equals 0 and x equals 1. So y equals x squared plus 2, we know that's a parabola, but I only care about the region between 0 and 1, so I'm just simply going to plug in x equals 0 and find the y value and plot the point. So 0 squared plus 2 gives me the point 0, 2. And when I plug in 1, 1 squared is 1 plus 2 is 3. So I actually have to go a little bit higher here. So I have the point 1, 3. And I know this is a parabola opening up, so my shape should be concave up. And there's a sketch of y equals x squared plus 2 from x equals 0 to x equals 1. For y equals -x, I'm going to change my color here and do it in blue. So if I substitute a 0 in for x, the opposite of 0 is still 0. So I have the point 0, 0. And when I substitute a 1 in, I get -1. So I have the point 1, -1. That's a linear function. So I'm going to do my best to draw a line. And if I want the area of the region bounded by these graphs, then y equals x squared plus 2 is my upper function, and y equals -x is my lower function. So all I need to do is find the integral from 0 to 1 of the upper function x squared plus 2 minus the lower function -x. And then in order to evaluate this definite integral, the first thing I would do is simplify my functions. So when I subtract a negative, that becomes a positive. So this turns into the integral from 0 to 1 of x squared plus x plus 2. And we really like that because it's a polynomial, which means we can use simple integration rules to finish. So the integral of x squared will be x to the third power times 1/3. The integral of x will be x squared times 1/2, and the integral of 2 will be 2x. Then I'll evaluate from 0 to 1. So I'll scroll down here. And you can see over here x to the third over 3 plus x squared over 2 plus 2x. When I evaluate, I substitute my upper limit first, so I substitute a 1 in for all my x's to get 1/3 plus 1/2 plus 2 minus my lower limit, but when I put zeros in, these all turn into zeros, so you can see in the work down here the lower limit values are not part of the scanned-in solution here. I'm just going to write a -0 just to make sure we know that that is a part of the process. And then I would simplify these, get a common denominator. That would be 6. So 1/3 would become 2/6, 1/2 would become 3/6, and 2 would become 12/6. So 2/6 plus 3/6 plus 12/6 is 17/6, and there's our final answer. I'm going to confirm this on the graphing calculator. So I already have my functions in here, and what I'm going to do is turn on the first function and the second function, and I'm going to change my window so that all I want to see is the region from x equals 0 to x equals 1. So I'm going to go from -1 to +2, so I have a little bit room on each side. And my y's, I'm going to go from -2 to +4, and I know that because I already graphed it by hand. And when I hit graph, here comes my parabola, here comes my line, and the region I'm trying to find the area of is in between those two. Unfortunately, on the graphing calculator, we're not able to find the area of the region between two curves, so we wouldn't be able to use the second trace integral option. Instead, we have to go to the main screen, and I'm just going to have to put something in here quick. There we go. And when I hit math and I scroll down, the 9th option is the finite integral. I want the finite integral of my top curve, which was y1, so I can go to vars, y-vars, and choose y1, minus vars, y-vars, y2, and that will subtract the top curve minus the bottom, not really curve because it's linear, comma, with respect to x, comma, from 0, comma, to 1, and when I hit enter, it gives me the decimal approximation, which I can convert to a fraction by hitting math and the first option. And there it is, 17/6. So finding the area between two curves is a relatively simple concept, an extension of what we've already done by finding the area of a region between a curve and the x-axis, which we've commonly said is the area under a curve. If I scroll down in the notes here, it would be like asking you to find the area of the region bounded by the graph of y equals 4 minus x squared and the x-axis. And the reality of the x-axis is that the equation for the x-axis is y equals 0. So I would really be taking the integral from -2 to 2 of my top curve, 4 minus x squared, minus my bottom curve, y equals 0. You'll see more of that as we do more examples, but this is the introduction to the area between two curves.